Bam. I said, bam. Ha! Who would have known a silly little picture like that would go so far?
I wish I had a video camera on my computer. I don't have one.
Oh, so you could broadcast yourself?
Yeah, I don't have one though.
Now the FBI can't watch you.
Yeah. I mean, I have on my laptop, but a freaking sunflower seed broke it, so I can't freaking use it.
How does a sunflower seed break a camera on a laptop?
No, it broke the screen. I literally was eating sunflower seeds in bio, and it falls on it, and I close the screen and just shatters the entire screen.
Oh my gosh.
Yeah, it's a
Well,
Mac
first of all,
too.
should you be eating sunflower seeds in bio?
Yes.
Yeah, bio's boring.
I can second
You go
that.
night
Bio
night.
is awful.
Thank you. All my bio.
Wait, were you talking about like in class or in online class?
In class, like when people actually saw each other.
So,
She had a whole like almost hour lecture of how not to fall asleep in class because
Yep.
it is that boring.
oh yeah, someone said that occurred. That lecture occurred.
Yeah.
Okay.
At least now
So-
I can mute her with my control.
Hey, wow. Wow. What do you got to say about me behind my back? Wow. All right.
Yeah, at least you're comical.
Oh, wait. Comical. Yeah.
You have a good sense of humor, okay? We don't sleep with your voice.
Not never sleep.
Can I get my there? Wait, no. All right. I guess I was trying to see if I could get the other list up here. That's fine. All right. No, I had a chat window or something. Oh, I could do it up here. Oh, am I sharing yet?
No.
Oh, well, it would help if I shared. No wonder it's not coming up. Well, we just had like 5 minutes of how do you do on that. There's my little thing to tell me when to stop writing. Good. Hopefully this is the right size. Maybe that's the right size. Okay. So I'm going to take this. I'm going to go over to, go back up there to a list, get rid of that talking. Come over here and show my participants. No, I didn't want that. I wanted the chat window open. My chat window. Oh. There we go. Now, just in case, go play your Game Boy Advanced SP. Come on, guys. What's that? Maybe I just don't even need to know this. If it ain't Diablo 3 or 5, I don't know what it is. Or Skyrim. All right. Seeing no questions about everything else because I never asked for them. Let's talk about buffers. Let me turn off this mouse so it doesn't move anything. Buffer solutions. Buffer solutions. Now we've been talking about in the plot. I'll just do oh wait, no, I can do that the other way. In a monoprotic, we had a curve that looked like this. And we said that this region, essentially from here to here, this is the buffer region. And that's where we would do the whole Henderson-Hasselbalch for the most part to get those points. Now, the one thing I did note about the buffered region back in the day is that over a wide variety of pHs, or I mean volumes, the pH did not vary. So if we look down here, again, we have our volume of our base and the pH. Over this whole region right here, the pH does not vary much. pH does not vary much. Now, the thing about buffer regions, and for those who've taken a bio class, you've heard about the phosphate buffer in your bloodstream and things like that. they're designed to resist changes in pH. So you notice that over that whole region, we're adding tons and tons of base. Nothing seems to be happening to the pH, or relatively nothing, right? It is going up, but it's not going up proportionally to how much base we're putting in. So what we want to do now is talk about if you wanted to actually make a buffered solution. So if you're in a bio class and you want to perform an experiment, the first thing you need to do is to control things. And biological materials do not like wide swings in your pH. If you think about working out, I'm sure this has happened to Tristan before. He's been lifting weights, and all of a sudden a muscle just cramps up. And basically that's his body saying, stop. You've put way too much lactic acid in your body to continue on. Up until that point, though, his bloodstream had, with its phosphate buffers and stuff, were trying to suck up all the lactic acid he was building up by lifting. And when it finally ran out of juice, when he finally gets over to a region where the pH does start to move, when he gets like over into here, that's when his body's like, hey, we're done here, okay? So let's talk about what it means to make the buffer. I talked about that region was governed by the Henderson-Hasselbalch, and there's a few ways of making these things. So remember, buffer region is controlled in the Henderson-Hasselbalch. Buffer region controlled via the Henderson-Hasselbalch. And so there's a couple of ways that we can talk about doing this. There is either by just using ingredients, titrating, or changing an existing buffer. So I'm gonna not worry about changing the existing buffer so much, because most of the time you would either just build it or just titrate it out. So for making a buffer, so when you're making a buffer, you got to remember that this is going to be from the Henderson-Hasselbalch. And I'm going to go back and just remind us that that is pH equals pKa plus log. Now, we've been doing x over A minus x, but what this really was the base over the acid. So when we were doing that x over A minus x, what we were doing is saying we have this much base that we have dumped in there, and we have this much acid left. That was the A minus x, okay? So a couple ways of doing this. You can do it by ingredients, or you can do it by titration. So by ingredients, this means you just go in the stock room and grab what you need and dump it in. Go to the stock room, grab what you need, dump it in. So that's if you just have the ingredients lying around. Now, if you happen to already have some sort of solution, well, then you might need to change it a little bit, and that would be titration. So by titration, this is where you use an existing solution and just move it along the curve. Just move it along the curve.
Does that just put in more acid and or more base until you get roughly in the middle?
Well, not necessarily roughly in the middle, but roughly where you want to be. And we will definitely be doing an example of that. So remember, if you just dump in a solution, it's naturally going to want to go to its equilibrium, which would be, its pKa, right? So if you need to be somewhere different from that, like, so let's say acetic acid is 4.74, but you needed a pH of 5, you would just add a little more base to just walk along that buffer region until you're sitting at that point. And then you'll let the whole equilibria take care of itself, trying to keep it at a pH of 5. And we'll do an example of that, so worry not on that. Again, you could change an existing buffer. It's a little more involved, but it's been done. It's easier, actually. Most of the time, people will either go to this, buy ingredients, just saying, look, I'm going to go to the stock room. I'm going to get my acid and my conjugate base, and I'm going to go ahead and just get a proportion there. Or I already happen to have this buffered solution. I just need to move it one way or another. So let's take a look. I want to do, let's make a buffer of pH 5. Let's just start with an example here. So, example, need a solution of pH equals 5. Okay. Now, what you want to do is you want to choose some sort of acid that has a pKa near that pH. So, choose, not chose. Choose a system means your acid or base near that pH, or whose pKa is near, and I'll go nearest, depending, to the desired pH. And the reason being is because if you dump in the right proportion of ingredients, it will naturally want to go to its pKa in the first place. And the closer you can be to your desired pH, the easier we are going to make our lives. So, first of all, what we need to do is we need to actually figure out what the ratio of the stuff might be. So hopefully you guys can see that at a pH of 5, our go-to one here is going to be acetic acid. I told you from the beginning, acetic acid and ammonia are the go-to examples of these. They're very well studied and very well understood. So we're going to start with one that we know very well. So we need a solution of pH 5. Choose a system, acid or base, whose pK is nearest to the desired pH. And let us consider acetic acid breaking apart to make H plus and AC minus, because that has a pKa equal to 4.74. So that's pretty close to that 5 that we want. I'm going to go ahead and well, shoot. Is there a way for me to, I want to try to move this thing a little bit here so I can, that's about as far as I can get it. All right, well, I guess that'll be my guide. Your chat window is getting in the way of my writing. I'm sorry about that. Okay. So what we need to do now is, if we go back to the Henderson-Hasselbalch, so we have pH equals pKa plus log of the base over the acid. We already know here the pKa, the pH we desire. We just need to get this ratio. Get this molar ratio. I want to remind us that this is a ratio based on the moles, not the molarity. So if we were to do this, we would say we have a pH of desired of 5.00 equals 4.74 plus log. And is it okay if I just do B over A for base over acid?
Yeah, that's fine.
Yeah.
Perfect. All right. Now, I also want to point out here that we actually know what the base and the acid are. What is the base in the above equation up here? We got this equation. What's the base?
Acetate.
That is correct. So we know that the B is the AC minus, And so what is the acid?
The H.
The H plus.
HAC.
The HAC. Remember, HAC is the acid, the AC minus is the base. The fact that H plus is split off is the byproduct. Okay, so check it out. We know what our pieces are. We just have to solve for some sort of ratio. So I'm going to go ahead and say that I want 100 mils of this stuff, okay? And sort of figure out how we're going to go about building this. So first of all, I should probably say pH 5. I go back up here, 100 mils of it. All right, what I need to do is pull over my 5, my 4.7, take the 10 to the power of to figure out what is my ratio going to be. So I do 5.00 divided by 4.74 is equal to log of my AC minus over my HAC. You'll go ahead and divide that out. We'll take a power of 10.
Wait, hold on a second. You're doing 5.0 divided by 4.74?
Oh, hold on, minus. What am I doing? Minus. So guess what? Thank you, Dallas. Glasses work well up close, not from afar. I guess I shouldn't have done that anyway. I should have just like done the math myself. Sometimes you want something done right, you gotta do it yourself. Plus log of acetate over HAC. I was wondering how 5.00 divided by 4.74 was going to give you 0.26.
That should be equals log.
Thank you. Do I need to drink some more coffee here? Oh.
Probably.
Chad, thank you. All right. Log of AC minus over HAC. Now, of course, to get rid of this at this point, we will do a 10 to the so that we can get rid of those guys right there. And we'll end up with that number being 1.81, oops. 1.81 is equal to the AC minus over the HAC. Remember, this is in moles. Remember, these are moles. Okay, and just to not to put too fine a point over it, it is 1.81 over 1. So we have essentially 1.81. So we need 1.81 moles of AC minus to every 1 mole of HAC. If we have that molar ratio, we're going to be okay. Now, this is where we get to dig our way back machine. How do you think we're going to get AC minuses? How are we going to get AC minuses?
We get the AC minuses from the HAC, and then we balance that with by adding.
And the reason why I say no is, remember, we're getting ingredients, so we're not waiting for someone else to give it. We're going to put it in there. How are we going to get AC minuses and HACs? What compounds would give this stuff?
HAC and what's AC and NA? ACNA?
ACNA? What is this one new message? That's weird. Oh, Lion Lee just types in NAAC. Yes, Lion Lee, you are correct. So NAAC gives us AC minuses, and an HAC solution would give HACs. Now I say an HAC solution because you're not going to find the dry ingredient of HAC. It is vinegar, it is a liquid, okay? So, but we can get the dry ingredient of the AC minus. So, I also want to point out something here. We can get our AC minus from the NaAC. We can find some sort of stock vinegar solution in the back. That's not a problem. But I do want to point something out about this ratio. Now we know where we're going to get them. Let's talk about their concentrations. We see this 1.81 moles to 1 mole. So now that we know where to get these stuff, the ingredients, let's look at how much. Let's investigate further. And here's what I want us to investigate. So we needed 1.81 moles of the AC minus in 100 mils of solution. That's what we sort of said right now. I'm gonna put this need in quotes. Now, if I were to actually dump in 1.8 moles directly, so we can do that, right? We can take sodium acetate and we can weigh it out and we can get 1.81 moles. And we could, and we'll do that with grams, right? We'll weigh out the grams, that'll give us the moles, we'll dump it into the 100 mils. Watch what happens. So we could, actually sodium acetate, do I have that molar mass? Hold on. 84.02 grams, right? If I did that to get 1.81 moles times 82 grams, that would be somewhere around 160 grams. We could use roughly 160 grams of NaAC. This will give 1.81 moles. Oops, running into my thing there. And dump it into our 100 mils. Does anybody see a problem with that?
That's going to change the volume.
Well, the
Yeah,
molarity,
go ahead, Chad.
I just said it changes the molarity. It's no longer 1.8. It's like 18.1. Right?
Yeah, so that's the kind of funny thing, right? So as Chad was saying, so first of all, Dallas says that much solute would change the volume. Absolutely. Chad says 1.81 moles in 100 mils or 0.1 liters is an 18.1 molar solution. Is that striking you one as odd?
Really strong concentration.
Yeah, kind of stupid strong. Have you seen anything that's 18 molar in your entire career here so far with me?
No,
No. And in fact, the closest you would have come is if we were able to have done experiment 6 where we use concentrated sulfuric acid. Consulfuric acid is 18.2. We've never seen that. That is just way too high, right? So this is way too concentrated. So I guess my question is, what am I doing to you guys? If I just made a problem that we can't do, we can't make this buffer solution, can we?
Well, don't you just need this ratio between the HAC and the AC? So couldn't you divide both by 10 and still have the same ratio?
Out of the mouths of babes. Dallas, good insight. The whole point about this, and I usually lead other classes down this road, and everyone's like, oh, feed me, I don't understand. Remember, what did we need? We needed this ratio. We needed the ratio, not the amount, okay? So we needed that ratio to be held consistent, not the exact amounts. So let me just go ahead and get rid of that and put that down there. Okay. We needed the ratio of 1.81 to 1, not the actual amounts. So, as Della says, why don't we just back everything up? One little thing. We've seen, so we could use 0.181 to 0.1. Ratio is conserved. So now if we have 0.181 moles of the sodium acetate, which is ostensibly our AC minus, in our 0.1 liters, this is a 1.81 molar solution, and this is doable. So here's what I'm going to say. We have sodium acetate in the background, and we have concentrated acetic acid. So in the stockroom, we have solid sodium acetate. Which is, yeah?
You have 0.181 divided by 0. liter.
Oh. Thank you. 0.1 liters. So in the stockroom, we have solid sodium acetate, 82.04 grams per mole, and concentrated 17.4 molar HAC. Do it. Okay. So what we're going to do is we're going to say, let's make our 100 mils of this. So we just said that we want, instead of 1.81, we'll do 0.181 moles of sodium acetate. So for the NaAC portion, we have 0.181 moles of the sodium acetate needed. We know that it's 82.04 grams per mole of sodium acetate. And that will give me, is that 14.85? Dallas?
Sorry, I have a quick little family emergency thing.
No, not a problem. What's more important, us or them?
14.85 for us.
Okay, cool. Hope everything's okay, Dallas. Okay, so what we're going to do is we're going to go to the balance. We're going to measure out 14.85 grams of sodium acetate and just let it sit off to the side. What we're going to do next is figure out just how much of this con HAC we need. So for the concentrated HAC portion, since it's already a liquid, we're not going to be weighing it out. What do you think we're going to do to it? If anyone were smart when they started hoarding food, they bought a whole bunch of this to put in their freezer. Concentrated juice. What do you do to concentrated juice?
Dilute it.
There we go. Now, of course, we don't have to serially dilute this. This will be totally fine. We know that we need 100 ml solution. We said that in the beginning, so we could say 100 mils. And we need, what is that? 0.1 moles per liter. But we're making 100 liters, so this is kind of interesting. This will be, at the end, a 1 molar solution, because we need 0.1 moles and 0.1 liters. So we need 0.1 moles in 0.1 liters. Right, that was our number of moles and our 100 mils there. And this will now go to whatever volume that is times our 17.4 molar solution. We'll see that our molarities here cancel. We're left with our volume. And the volume we need is going to be 5.75 mils. And we're going to dilute to 100 mils. So at the end of this day, what we're going to do is we're going to take that 14.85 grams of sodium acetate that we set off to the side. We're going to take 5.75 mils of the concentrated acetic acid. We're going to put those into a volumetric flask, and then we're going to just dilute everything to 100 mils. So put 14.85 grams of NaAC and 5.75 mils of concentrated HAC into a volumetric flask and dilute to 100 mils. When we look at this, what we want to take a look at is, first thing is to figure out what the molar ratio is. The second thing, figure out if it looks reasonable. Is it too concentrated? Is it doable with the ingredients you might have? And then just figure out what you might have. Now, I'm already going to answer the question there, Tanaris. I will tell you, if it is necessary, what you have available to you from the stockroom. If I don't tell you, the answer is sodium. Just as Lion Lee said sodium acetate, he goes, look, we know that we have things like this. We should always keep those in mind. So let's go ahead and do another one of these. I love / hate this one. I love it because it is the phosphate buffer. I hate it because we have a whole bunch of PO4s running around. We got to be very careful. in how we do it. So without further ado, I'm going to pull this a little closer so I'm less likely to make a mistake with all my HPO4s running around. Okay.
Forrest, I have a question.
Who's that?
Kimchi.
Hey, Kimchi.
Hello. So when you have the HAC solution, does it like kind of break up into H and AC? And like how does that affect how much AC you put in, or it doesn't? I don't know.
It doesn't, because remember, look at how many moles we're putting in, 1.81 moles of this AC minus. Remember that the HAC, sure, it's broken up. Sure, it's giving you stuff. And remember, it's breaking up to 1/10,000th.
Okay.
And we're putting in 1,000 times more than whatever was sitting in the background. So again, I can't remember who I told this to back in the day, but and I can't remember if it were class or an office hour, but someone said, hey, but this thing's already breaking apart and doing its thing. Like, what do you mean we're pretending it's zero? And we're going to pretend it's zero because the amount that we're going to end up generating or adding on the back end completely dwarfs whatever HAC is doing. So when we did those problems, we're like, hey, what's the pH of this 1 molar HAC? And we start out the ice table and we say, all right, we got 1 HAC. And then we have 0 H's and 0 AC minuses. Dallas loses his mind and goes, that's not true. It's been sitting there. It already is at equilibrium. We already have AC minuses. What do you mean there's none? And then we go through and we do the whole equilibrium table and we find out, yeah, there are some. And they're in the 10,000th range. And so when we say we have a 1 molar solution, that is untrue. We are just saying, look, it is insane to go through and actually say that really it's a 0.99997 molar. Okay, if we really want to make 1 mole, we have to add in just a little bit more, a little more concentrate. It just becomes a nightmare. So we say it's a 1 molar when we know that there are 3.16 10,000ths of those things floating around already, but they are dwarfed by anything else we might add to that solution. And that's why we're ignoring into the ACs that would have come off of that HAC, because that sodium acetate is just dwarfing everything. Just saying, look, thanks for contributing. I got it from here. Does that make sense?
Yeah.
Okay.
Thank you.
Not a problem. All right, let's create 100 mils of a buffer with a pH 7. Let's create 100 mils of a pH 7 buffer. Now, I'm going to look in a book because I don't know how to use these internets and this fancy technology. I'm going to look in a book and see that phosphoric acid has a pKa of 7.21. Technically, it's a pKa 2. Now, that seems to be a reasonable place to start, and it better be because this is my example and it better work. Now, could you find another one that's close to 7 and use it? Sure. Whatever you do, knock yourself out. You just want to make sure that its pKa is close. Now, I did call it a pKa 2, and that is because it is really already the H2PO4 minus going back and forth make H plus and HPO4 2 minus. So we're actually in the second, we've already gotten rid of one H, right? That H2PO4 with a minus has already lost one of its H. So that's pKa 2 is equal to 7.21. Now, Lion Lee, can you think of where we're going to get these ingredients? Now, first of all, let's double check what our ingredients are. Let me make this look a little prettier. What are the ingredients that we need, chef? Look, just because I can't see you doesn't mean you can hide from me.
HPO4 minus.
Mm-hmm. That is the acid or the base?
The acid?
That is the base.
Oh.
And how do you know that? Because you have an H plus sitting right here. That H plus is the acid. Acid plus base equals your other thing. Okay?
Oh, yeah.
So, you know, again, all we have to do is remember what we're looking at. So we need HPO4 minus and we need the H2. So this is the base. And this is the acid that we need. Okay? All right, Lion Lee, tell me, where am I going to get those? I swear, if you type it, so mad. All right, type it. The store. Okay. The store. I was hoping you were going to put that sodium in front, Lion Lee. Thank you, Captain Obvious. The store. Your instructor. All right, there we go. So Lion Lee's right. We can get H2PO4 minus and HPO4 2 minus using their sodium salts. You know, I swear, if I have to do this online in the summer, straight from like not knowing anybody, this is going to be so dull. Because at least now we can razz on each other. It's kind of fun.
Forrest,
Huh?
could you confirm that we're not going to go back to school for the rest of the semester?
Oh, wait, that was already sent out. Yeah,
Okay.
that should have already. Who was that?
You
Yeah, I
said?
already received the email that we're not coming back until the end of the semester.
Yeah, they sent out a little bulletin. So if you didn't get it, it's probably because they don't love you. But yeah, no, they sent out a thing that says, "Good luck. Thanks for all the fish."
Yeah, this sucks.
Who said that?
Garrett, Mays.
It sounded like it was a raspy Dallas there for a second. I thought Dallas was catching a cold. Yeah, no, it sucks. But you know what? I think if any class can get through it, it's going to be us because we kick ass. And I think we're having a lot more fun than most classes are in trying to get through this. So let's just keep having fun. All right. So let's take a look. We needed that pH equals pKa plus log of the base over the acid. Our pH that we wanted was 7.00. Our pKa was 7.21. And this is now going to be log of the base, which was the HPO4 2 minus, over the acid, which was the H2PO4 minus. You can see why I both love and hate this example. There's going to be lots of H's and 2's and PO4's and not in the same spot. But it's a very pertinent one that we need for blood chemistry. So we have 7.00 minus 7.21 is equal this time, not plus, is equal to the log of the HPO4 2 minus over the H2PO4 minus. And so that means that is negative 0.21 is equal to the log of the HPO4 2 minus over the H2PO4 minus. Now, very first time I did this problem, I balked, I stopped. I was like, wait a second, what do you mean a negative number? Is that going to give me some sort of weird error message? And it turns out it doesn't. It's totally fine. It just gives you something that's less than 1. So don't be afraid if you see that negative number. Again, we're just going to take the power of 10 to these things, which is going to get rid of those guys. And at the end of the day, we end up with 0.62, I believe.
Yeah.
So we get 0.62 is equal to the HPO4 2 minus over the H2PO4 minuses. And of course, let's remind ourselves that it's over 1. Now, just to note, let's check it out. 0.62 moles of the HPO42 minus in a 0.1 liter solution. That would be a 6.2 molar solution. Chad, what do you think about that? A 6.2, is that doable? Just say no. 6.2, well, it might be a bit much. Now, side there probably going, how am I supposed to know what is too much? Like, how am I supposed to know? Let me channel my inner Dallas. How am I supposed to know that? So, was that a pretty good Dallas, by the way?
It was acceptable.
Thank you. How do I know 6.2 molar might be too much? Okay. Hey, remember that solubility stuff?
Vaguely.
What does it mean to be soluble? Does anyone remember? I probably only said it in passing, but what does it mean to be soluble?
Dissolves in water.
Dissolves in water, but there's a certain concentration threshold. And I probably have only said it in passing, so I just wonder if anyone remembers from in passing. Soluble is defined as a 0.1 molar solution. Now, had we been able to do experiment number 6, the carbonic acid salt, in that experiment, you would have taken some concentrated sulfuric acid and some baking soda. You would have neutralized those out, generating a ton of carbon dioxide gas. That carbon dioxide gas, you bubble through some water to make carbonic acid, okay? At the end of that, what you would end up starting to do is playing around with different solutions, and you would find that one of them would not be very soluble because it was just below the 0.1 molar solution. And you'd be like, oh, nothing's happening here. And in fact, you guys have actually already seen this phenomenon when we did the Le Chatelier lab. You watched your silver acetate come and go. Now, that's because silver acetate can actually make a 0.11 molar solution. So we're talking like it is 0.01 barely into being soluble. So it didn't take much to make it insoluble and then come right back into solubility, which is it crosses over that very fuzzy threshold of 0.1. For those who took Chem 110, I'm going to set the Wayback Machine for you. If we did the types of reactions where you did the single and the double and you neutralized things, so virtually raise your hand if you were to pretend that Meng and Garrett and maybe a couple of others, Loban, I don't remember if you were in 110. we were always supposed to see a precipitate. But one of them, you didn't necessarily see one, and that was the calcium sulfate solution. And the reason for that was at room temperature, it will just be right on that cusp of the 0.1. If you get it just warm, you will actually make it that actually goes backward from what you would think about soluble being more soluble and hot. Turns out calcium sulfate, when you get it hot, it becomes less soluble. There are a few exceptions to every rule. But that one was also one that some people saw and some people didn't because it was right on the cusp of the 0.1. Now, that was a long-winded, dry story without all my cool animated antics out there, just to say, look, skip to the end, Basil. The idea here is that 6.2 molar might be a bit too much. We want to get that 0.1 area. So why don't we go to a 0.062? So let us go to 0.062 molar.
So you're saying that 0.1 molar is like the minimum for soluble stuff.
Yeah.
And then presumably there's not necessarily like a maximum, but like, so where's our, like, how are we telling what's like, okay, this is a bit too much here?
So yeah, and that is a good question. So when you decide to make your solution, when you decide to figure out, okay, am I making a liter, 0.1 liters, 0.2 liters, when you take this ratio right here and you say, I need that many moles in that solution, if that molarity here is above 0.1, you want to back down the number of moles, or you could increase the volume of the solution, but that's just being wasteful. You want to back down the number of moles so that you can actually get this thing to look like a reasonable concentration. So what I've done down below is I said, look, that's way too much. So why don't I get, instead of 0.62 to 1, why don't I change it by a factor of 10 and get it to the 0.062 to 0.1. And the reason I'm going to do this is because, did I do that? Is enough? I think I did. 0.062. So that's going to go 1 to 0.1. Yes, I moved those correctly. So let's go to this. So what this means is we're going to do, this will now become a 0.62 molar solution, and this is a 1 molar solution. And each of those will be acceptable. And the reason why I say the 1 molar is because it is a sodium compound, so we'll be okay with that. If you get everything to 0.1s, you're going to be fine, okay? If you have 1 molars, okay. What you don't want to get into is the 5, 6, 7s, and 10s. So I'm going to choose this ratio. Now, immediately the questions are going to be on the exam, like how am I going to know what's the right ratio? What's the right concentration? I'll tell you right now, buffers take a long time to get used to, and as you do the homework problems, you'll get more familiarity with it. But I'm going to be reasonable on the exam. As long as you're not trying to make a 10 molar solution of something or making it just way too concentrated, I will be okay. As long as you're not going to try to take everything down to the 0.01 molar concentrations and things like that, I'll be okay. I just want to know that you guys understand the concept of building these or titrating these more than the actual numbers. When you finally get to making them in real life, someone is going to teach you a much more in-depth and better way of doing this. I mean, even down to the point where in order to save materials, you may be using micro pipettes that are like stupid awesome, where you can get like 0.02 mils and just drop it in there. And so I'll leave the technique of this to future endeavors where you'll actually be physically doing it and physically making them, because that's where it'll become real. Right now, I just want you to realize that there's a method to it, and this method involves choosing a pK very close to your pH, and then just slightly adjusting that base to acid ratio such that you would end up with that value. Does that make sense, Dallas?
Yeah, I think I get the idea.
Okay. I guess I should say, does that make sense to everyone else?
Yeah.
Okay. So let's take a look. What I want is 0.062 of the HPO4s and 0.1 of the H2PO4s. So let's get our ingredients. So we need 0.062 moles of the HPO4 2 minus. And we're going to put that, we're going to make that concentration. And we're going to make 0.1 liters of that solution. All right, so we wanted that 0.062 to 0.1 ratio there. Now, we need on the bottom here 1 mole of the HPO4 2 minus will come from 1 mole of Na2 HPO4, and then the 1 mole of the Na2 HPO4, 1 mole of Na2 HPO4 weighs 141.78 grams of the Na2 HPO4. So this is our standard mass to mole to mole to mass. We've done these ad nauseum through Chem 120. In the end, that says it's 0.865. So 0.865 grams of Na2 HPO4 are needed. The other telltale sign, guys, especially with dry ingredients, you should be looking at masses that are what you would go weigh out in the lab, okay? The problems I will give you will have reasonable benchtop volumes. You notice that I've chosen 100 mils here again. I've chosen that 100 mils because that's what you would probably use in a lab. When you go to the balances, 0.865, that seems like a reasonable value that you would measure out. So this right here is telling you you're probably on the right track. Let's do the next one. We needed a 0.1 molar solution. So 0.1 moles now of H2PO4 minus per liter. We're going to make 100 mils of that. And, you know, just to be thorough, I'm going to show the molar ratio. If you guys don't show this molar ratio of the 1-to-1, I'm probably not going to get you. You know, at this point, we should be big boys and girls enough to know that we have these ratios. However, heaven help you if you get that ratio wrong somehow. That's all I'm going to say. So 1 mole of H2PO4 minus for every 1 mole of NaH2PO4, and 1 mole of Na2HPO4. Oh, sorry, I told you, NaH2PO4, sorry, is 119.98 grams of NaH2PO4. That will give you 1.2 grams. Okay.
Wait, I have a quick question. Why is the mass of the NaH2PO4 different than the first mass?
See, this is why I said I love this and I hate this. Pay close attention here, Kyra. Ready? Na2H, NaH2.
Oh, I see.
And you know what? Every year, and this is why I say I have a love-hate relationship with this one. It is the example that you need to use because it has so many applications in bio classes. But man, if you don't have to keep track of who's got the two and who doesn't, and every year I look at my stuff and I'm like, why are those masses different? Wait, why does that one weigh less? Oh, that's right. We lost a sodium and exchanged it for a hydrogen. So I just asked myself the same question. I just didn't let you know I was asking myself that, and I did that today too. So good question.
Hey,
Yeah.
Forrest.
What?
We're multiplying by 0.1 liters of solution because we want 100 mils of it, right?
That is correct.
Okay.
That's correct. So we're looking at making a concentration and then how much of it, and then figuring out how many moles we're putting into that solution. That's why we're saying that 100 mils of solution.
Got it.
You can't just say, oh, I'm putting this many moles in, because you need to know into what.
Yeah. Okay.
Chef, I think I'm screaming too.
Yeah, I just got a slightly different answer for the first one.
Oh, you're wrong.
All right.
No, I'm kidding. What'd you get?
I got 0.879.
Confirmation? Dallas? Oh, wait, you may not be back yet. Lim? Oh, you ditched us.
I got the same thing.
As me or
Yeah.
her?
0.879.
0.879.
Well, then, okay. What the heck?
Is it still from the book?
Oh, no, I know what it is. It's fine. 879?
Yeah.
Okay. The reason is because when I first did this problem, and I should have realized when I had a red line on it, is it shouldn't, I had an 861, because years ago when I did this problem and I just flippantly did it, I relied on somebody calculating they had 861. Nobody said anything for years. And then someone goes, actually, it's like 8618 or something like that. And so I rounded it up to 0.062, but I never changed my original 061. So my 061 would have given us 865. The 062 gives us 879. Thank you guys for, man, I taught you too well. Always question. I taught you too well. Thank you, Chef. Look, that'll make us happy. Okay. So at the end of the day, what does this mean? You're just going to take 0.79 grams of the sodium hydrogen phosphate and 1.20 of the sodium dihydrogen phosphate, and we are going to just mix them in and dilute them up. So put the solids into a volumetric flask. Add a little bit of water. Add some H2O, mix, backfill to 100 mils.
And to be clear, we don't need to worry about this thing trying to make H3PO4.
Oh, it will. Oh, it will. And it's going to make PO43 minus. But again, so little compared to what we have just dumped in that they are going to be negligible. Does that make sense?
I get the idea behind it. I don't see how that will be true for this particular case.
Why not?
Because from what I remember, in those like multi-H acids and whatnot, the earliest ones, in this case H3PO4, is usually like the dominant one.
Yeah.
So
But we're gonna move in there. So I'll probably actually answer your question here as you keep asking it. Go ahead, keep going.
So yeah, so it seems like where we have the H plus and HPO4 and whatnot. If you have an enormous amount of the H2PO4 and whatnot, wouldn't you expect it to be like, oh hey, let's quickly make a lot of H3PO4 when we have none to begin with?
So I totally get what you are trying to say, but I'm going to start putting down here. So many of you see that I'm already writing down here while he's talking. I'm going to go ahead and write down all three of these because I just happen to have them sitting right next to my notes. And I'm going to continue on with the other workhorse of the people like to use a lot, mostly because they're well understood and or they're very, very common. And that is, I'm going to put the phosphoric, the acetic, and the ammonia. I'll do acetic acid and ammonia here last after I answer Dallas's question, or hopefully answer his question. So while you are correct, Dallas, that the first pK is the one that dictates predominantly the pH of the solution. And that is, I have phosphoric acid. Yes, its pH will be somewhere around 2.12 because that's what it wants to do. pH equals pK. It's going to go right to its equilibrium. Done. Okay. I don't like your argument of like, oh, well, since that's the case, then if we happen to be somewhere else, it'll always go back to its beginning. Because keep in mind, this is what we've actually done here, Dallas, is we have taken this sort of thing. We've gotten our little titration curve, and we've gone up. Oops, I want that in purple. Hold on. We've gone up and up and up, right? And we've got our endpoint 1, endpoint 2, and endpoint 3. And I guess my thing is, hopefully this will answer your question. This guy right here is 2.12, 7.21, and 12.67. And what we have just done in the previous example here is we said we wanted a pH of 7. So we decided we're going to move right here.
Yeah.
Are you okay with that?
Well, in theory, yeah.
Just with the idea that as we did this, all we said is we want to be right there on the curve. Yes?
Yeah.
Okay. So what we have just done is we have made sure that we added the precise amount of ingredients to stick us right there on the curve. Can you agree with me there?
No.
Why not?
Because doesn't being in that area of the curve rely on there already being, a bunch of H3PO4s and stuff having been there and deleted?
So I think I see where your question is. So first I want to say we have added the ingredients to put us right here in the orange circle on this curve. Okay.
All right.
And I hope everyone else can agree that that is what we just spent all this time doing, was to add the precise amount of ingredients to put us precisely there on that curve. All in favor, say aye.
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 Okay. Now, what you're confusing here, Dallas, and we will actually do one of these here in a minute, is you're confusing plopping ourselves down on the plot versus getting ourselves there on the plot. So what I mean by that is we've spent the last couple of class periods building these titration curves, starting with the acid, the full-blown acid, and only the acid, and slowly adding base to move ourselves along the curve. And we will do that here in just a moment. And it might even be our next example. If not the next, it'll be the one right after it. And that is, normally we have started at just H3PO4, kept adding base, kept adding base, kept adding base, and we were like just marching ourselves along this curve until maybe we get right there. That's not what we're doing here. What we're doing is we're saying, go right there, bam. Not get us there, put us there. Keep in mind, when we did Henderson-Hasselbalch, okay, when we did Henderson-Hasselbalch, we chose that base interval to use. Why? Because we'd say, like, let's pretend we jump here, then pretend we jump here, then pretend we jump here, and pretend we jump here, and give us all of those points along the curve. And if you recall, I said we're going to pretend that we jumped 20 mils, jumped 40 mils, jumped 60 mils into here. Well, we're going to do exactly the same thing by adding ingredients. We're going to jump straight to orange circle.
All
And
right,
once again, go ahead, Dallas.
all right, I think I get the idea.
Okay. Now, again, the other thing too is you go like, well, why doesn't it just slide all the way down to the bottom again? Why doesn't it just go back to that original starting position? Well, keep in mind, equilibrium says that it's not even going to go to the starting position. It's probably going to go to that pKa. It's probably going to go to its equilibrium where it wants to be, right? When everything is all said and done. Going and jumping regions is actually pretty much forbidden unless you do something to move it, okay? And you can do that, but in a buffer situation, you don't want to have to do that. And what I mean by that is you never start with your ingredients, say, over here somewhere and say, oh, now we're going to add enough stuff to get you here. You would never want to go and jump over regions. It's possible, but man, you don't want to do that when you are just plopping yourself down. Okay, we'll talk about moving ourselves from the beginning to this point when we get to the titration version of doing this. But what we've done here to try to bring it back full circle is we've said, look, we want a system that has a pK close to that. And yes, the phosphoric acid buffer system does. It just happens to be the second region. All right, it just happens to be the second region, but that's okay. We can add the correct number of ingredients into the second region, and that is the H2PO4s and the HPO4s, and we'll plop ourselves right there. If we wanted region one, say like a pH of 3, we would not use the second one, but we'd use the first ingredients. If we wanted a pH of 12, we would use the last set of ingredients. But what we wanted was this guy to put us right here. And that's why we use those ingredients. So we could have put ourselves anywhere on this plot, anywhere we wanted. We just have to choose the right ingredients, which will put us in that pKa region and then move us around a little bit to get to where we need to be. Now, in this case, we made a pH 7. And depending upon your volume and your concentration and what you're doing to it, the solution now has the ability to try to move back and forth within this buffer region to keep somewhere near that pH of 7. Clearly, you can see that we can't get too much more acidic or we'll drop off into the other region, but we have now plenty more room to move in the basic region while still keeping our pH around that pH 7. So all we've done when we make a buffer is we're to the left or the right of the pKa, and you can move more or less depending upon which direction you're going. Let's look at a couple of other common ones here real quick too. I told you I would just go ahead and put up the other two workhorses. Phosphoric acid is great, and of course we keep working with acetic acid. So HAC, back and forth to make H plus and AC minus. This has a pKa, oops. pKa equal to 4.74.
For it,
Kenji?
are we ever going to be using like a base and then adding acid? Does that make sense? I don't know.
Look at this. Sort of. Would you ever use a base and add the acid? Yes. Let's say that you want to be in this region 3 for some reason, for whatever reason.
Mm-hmm.
Let's say you want to be in there. You would technically be using the base to get there. And then you'd probably add a little bit of acid if you wanted to drop the pH down. So if you wanted to go this way, you're talking about adding in acids. If you wanted to go this way, you just add some more PO4 3 minuses.
Right. But we're not using like PKBs, right?
No, I wouldn't do that. Convention says work with your pKas and go accordingly. You can talk about it in terms of bases. It is just a mind flip. I just don't like confusing that issue because I don't think there's any benefit to it. I mean, let's face it right here. What did I do? I put the ammonium ion back and forth to make H plus and NH3.
Mm-hmm.
Well, we know that, take a look at that pH. I mean, pH is pKa. We are a base when we're looking at this.
Yeah.
And so what happens if we wanted to make 300 mils of a pH 9?
You would use NH4 and NH3.
Make 300 mils of pH 9. I can make a better 9 than that. Right? In that case, we're going to be looking at using this NH4 plus. So in this case, we are going to be using the acid version of what was a base. You know, ammonia is a base, but we'll use the acid version of it just because convention says think about things in terms of pKas all the time. Even up here, when we talk about this HPO4 2 minus making phosphate, we're still calling it pKa. We're still talking about it in the acidic form, even though it's a base. So convention says keep everything acid, 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 so we don't have to do this mind flip later.
Okay.
Just like hot goes to cold, period. Always think about it that way. So let's take a look. Let's do pH equals pKa plus log now of NH3 over NH4 plus. Right, because that's going to be our base and our acid, right? So that's our B, and that's our A. We know we want our pH to be 9. That pK was 9.26. Plus log of NH3 over NH4 plus. If you don't mind, should I just skip to the end on the ratio, or do you want to see all the math?
Math.
Okay. Somebody say math, or I'm going.
Math.
No shit wants to see it. Okay. So 9 minus 9.26 equals log of the NH3 over the NH4 plus. Do I have to say that that's negative 0.26, or are you guys okay with me doing this? Garrett, you all right?
Yeah. Yeah. Hello.
Right.
Yeah.
Perfect. So that'll end up giving us 0.550 is equal to NH3s over NH4 pluses. So always look at the biggest one. So 1 here happens to be the big number. The 0.55 will always be less. So if we get the 1 to look like a reasonable number, then we'll be okay. So look at biggest number in ratio. If it is okay, then the smaller one will be too. So I'm going to look at 1 mole of NH4 plus in 0.3 liters of solution. This will give us a 3.33 molar. You guys like a 3.3 molar? Isa, you're awfully quiet. Don't make me unmute you. Is Isa still here? Oh no, did I lose Isa?
I mean, it says she's still here, but
No,
she's
sorry, I went to the
also muted.
restroom.
Oh, okay.
What happened?
It's so funny. I was talking to another teacher friend of mine. She teaches elementary school, and she's trying to do the online thing and everything. And she says, yeah. So there was a kid raised their hand in chat, and she's like, okay, yeah, what can I be excused to go to the restroom? And I thought that was adorable. You know, and it was funny because in my Chem 110 class, one person was like, hey, can we build in some bio breaks? And I was like, what? We're not in bio. And they're like, oh, you mean to go potty? No one's gonna know if you just up and leave for a second.
Yeah, sorry. Should I raise my hand next time?
No, you know, and that's no, you don't need to. That's the funniest thing of it all, because during a normal class period, you're like, whatever, you just get up and walk out, slam the door. You don't think twice, but now you're like, can I ask to go to the restroom? It's pretty funny. So anyway,
What were
Isa,
you asking?
so the question was, does a 3.3 molar NH4 sound like a reasonable number that we could use?
No.
Why not?
I would go smaller.
Yeah, you might as well go smaller. Now, to be fair, I would actually say you're wrong. No,
Oh, okay.
no. If you remember, the ammonium solutions are incredibly soluble. Those are our sodium, potassium, and ammonium. You
Right.
could be molar. You could, but I like your line of thinking, and that is no. Let's take it down a notch. Can we at least just take it down to 0.3? I think that's probably reasonable.
Yeah.
Hey,
Yeah.
real quick, can you scroll up for a second?
Yeah.
All right, you're 0.26. Go
Yeah.
up. You just took
No,
your
you-
zero. Oh, negative 0.26. Okay, I'm sorry.
I figured that's what.
Yeah,
Trust
yeah.
me, I've done that at least 10 times teaching this class. And that was before classes. Imagine now. All right, so Isa says, oops, I need to immortalize you in here. Uh-oh. Uh-oh. Hold on. I'm gonna do this. Hold on. Shoot. Where are you?
2 semesters and you don't know how to spell my name?
What? No, I totally remember. You're calling me out on live video here. Issa says, make it 0.333 molar. Call it done. Because ammonium is so soluble. So we'll just back everything back a bit. By the way, I did not do this in my notes, so I'm going to need your help. So this is now a 0.0550 to 1 ratio of NH3 to NH4 plus. Actually, that should be 0.1. So we'll back everything back by 1, right?
So that's just a calculation that doesn't matter, right?
What do you mean?
I mean, because we're still going to keep our 100 milliliters.
300 mils.
Or 300 mils.
Right.
Okay.
Right.
I don't know.
Yeah.
Just keep going.
No.
Well,
Slow
I mean, every time that we've changed our calculation or changed our concentration, we've never done the math because it's nothing that volume doesn't matter. Am I right?
So when we're doing this, so you know, let me just sort of finish this out. So this guy, ammonia, this is going to be a liquid and probably 6 molar. And this guy right here is going to be a solid. And we'll probably do something like NH4Cl. Okay. So does it matter? Yes, but what all this is really going to do is shift everything backwards. So I can already hear Dallas in the background going like, well, why don't I just take whatever ratio I happen to have, calculate how much I need, and if it's too much, just move everything back a decimal or 2. And the answer is yes, you can do that once you have your initial amounts. We're just right now moving the decimal back early so that we don't do it later. It just depends on when you want to move that decimal. So what I mean by this is 3.33 is perhaps a little high. 0.3 looks a little more reasonable. So instead of needing 0.55 moles, I'm going to do 0.055 moles. And instead of having 1 mole, I'm going to put 0.1. And all this is doing is making it less concentrated, but still maintaining that ratio. The ratio is the important part here. You must maintain that ratio. So we can take do this sort of thing. This liquid here, we would do this by dilution. And the blue, just weigh it out. And then combine them. Oh, look, and yellow and blue makes green. So we could do that, 0.1 moles of NH4Cl. We need that concentration per liter of solution. We're going to have 0.3 liters of solution. That's our 300 mils. And we know that 1 mole of NH4Cl weighs, I don't know, what is that? Chlorine is 35, 45, 49, plus 4 is 53. 53, 35 plus 5 is 53, 40. Can somebody confirm that? Somebody over there has their, okay, Google, ammonium chloride mass.
Yeah, 53.4.
Dang.
Well,
Yeah.
actually, it's 53.49. So if you want to bump to 53.5.
4.9. Oh yeah, of course. 4.9. 3.5.
That's what Google says.
4.9. Chlorine's 35.45, not 3.5, 4.5. Yes, 4.9. Yeah, sorry. I just, I'm just pointing out that I did that from my brain, from my memories. So somebody give me those grams.
1.60.
Hey, does that seem like a reasonable number, guys?
Yes.
Yeah. And then let's assume we had a 6 molar ammonia sitting in the background. So, and we needed a 0.055. So 0.0550 molar. We're going to make 300 mils of it. And this is going to come from 6 molar. So the question is, how much do we need? That volume 2 is going to equal
2.75.
Again,
2.75.
2.75 mils of 6 molar NH3.
Where did you get the 6 molar from?
Oh, I just assumed up here I said probably from 6 molar. Stockrooms like to have 6 molar solutions on hand. Don't ask me why, but we like to have 6s and 1s. I just assumed this. That's the whole probably. I would give that to you on the exam. The only thing I wouldn't give you is, hey, clearly this is like, the NH4, where are we going to get that? I would hope by now that you guys have sodiums and chlorides as your go-tos, or even nitrates if you have to get you the other portion. You should be able to recognize when something is could be a solid or is definitely going to be a liquid. Now, to that end, what I did for my Chem 110 exam is I hung around for 4 hours in a chat room in case people had questions, and they would privately send me a question, and I'd privately answer that question. So I will be doing that for you guys too. So when in doubt, raise your hand / get on that chat window.
Hey,
what?
so just to be clear, the actual physical process here would be you take the 6 molar and you take 2.75 milliliters of that, dilute that out to 300 milliliters by adding water, and then dump in the 1.6 grams, correct? That's the sequential process?
Chloride and 2.75 mils of 6 molar NH3. Some H2O. Mix. Backfill. To 300 mils. Now, the interesting thing is this time I decided not to say like, you have a 300 mil volumetric flask. Let's be reasonable, guys. You have yourself a big graduated cylinder, and I mean they make some big ones. There's a 2-liter one in our stockroom if you really want to get down to it. So let's say that I take the 1-liter graduated cylinder, okay, and I'm going to fill it up to the 300 mil mark. So what's the worst that I could be off? 3 mils, 2 mils? Is it really going to make a difference for the concentration?
Not really.
No.
No, it's not going to make a difference. So in the 100 mil situation, it might make a difference because we're starting to get to small enough volumes that you want to be very careful. When you start making larger volumes like this, you don't have to be as precise with your glassware because anything that you're going to accidentally over or under fill is going to be negligible in the grand scheme of things. So that's why I didn't say a 300 mil volumetric, because A, they don't make them. B, it won't matter. They do make 500s and thousands if you're trying to be really accurate. But look, this is a buffer. We're going to get around that region. It's going to be okay. All right. Let's see. I wanted to do one by titration, and then maybe I will give you one for homework, depending on how much time we take here. I can tell you right now, Kyra, yes, we are not getting to that exam until after the break.
Okay.
I don't know if anyone's noticed, but these lectures are taking a lot longer online than they are if we were in person.
When is our break?
I don't know, the 6th.
Okay.
Next week.
Next week. So, I mean, I would love to power through, but I think there are many people who'd kill me along the way. All right.
For
The
sure.
other way to do this is by titration. Okay. What that does is you already have some sort of solution sitting there. And all you have to do is sort of move it left or move it right, as long as your solution has that pKa somewhere where you are, or could have a pKa somewhere where you are. Let's say if you started with something too concentrated. So I'm going to do this by example, because that's how I do everything. We want to make and I'm going to put this in parentheses, at least 100 mils of a pH equals 4.5 solution. And we're going to do this from a 1 molar acetic acid and a 0.4 molar sodium hydroxide solution. So really what this is asking us, how much sodium hydroxide do I need to add 1 molar HAC? And then let me rephrase that. That should be a 0.4. Do I need to add 1 molar HAC to get to pH equals 4.5? That's what that's asking us to do. Now, let me go in case people are writing. Now, what I could do is say, okay, well, I have these ingredients, V1, figure out the total moles, and then something. The problem about that is, since these are both liquid solutions, you might have a problem getting to the right volume. So let's go back to thinking about this in terms of a titration. And so what I mean by this is we go back to pH is equal to pKa plus log of the base over the acid. Well, in a titration, we know this as pH is equal to pKa plus log of X over A minus X. So let's use that guy. Now remember, X is the amount of base and A is the acid. And I'll point out some of the specifics about how I wrote that in a second. So this is going to be 4.5 equals 4.74 plus log of X over A minus X. Now, A, we can do this. We knew that it was 1 molar HAC, and how much did we say we needed at least?
100 milliliters.
100 mils. Okay. The reason why I said at least is because as long as you start out with said requisite volume, you will be guaranteed to have that volume by the end of the day. We're going to be adding more liquid, so we're going to be making more buffer than we need. But if we start with our original, how much do you need, you will never run out. You will never be cut short. And Dallas, save that question for the end. Lim, save that for the end. I know you're not here, Lim, but I'm still going to pick on you because you'd say the same thing Dallas would. So what we're going to do is we're going to figure out, we know the A, we know the pKa and the pH that we want. What we're going to be looking for is what the question asked us is, how much base are we looking for? So we're going to look for X. So we come back down here, we subtract it out. So we have 4.5 minus 4.74 is equal to log of X over now 0.1 minus X. So that is negative 0.24 is equal to log of X over 0.1 minus X. We're going to take the 10 to both sides on that. And so we get 0.5754 is equal to X over 0.1 minus X. Raise your hand if you want to see the rest of the math. Seeing no hands. Let's see.
I want to see it.
Who was
Math.
that? Whoa, 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 whoa. Who said you could come, Tanaris? Showing up like a ghost. I like
Been
it.
here for a while.
For a while, but not the whole time. We were looking for you. We were like, "Where's Tanaris?" And I
To
said,
be
"Ah,
completely honest,
he's probably just
completely
gonna."
honest, I didn't hear my alarm.
Yeah,
So
I figured you were sleeping enough, so
yeah.
I figured you just wanted the extra sleep. That's okay. I did too. I just have a job to do. Trust me, I did not want to wake up this morning at 6 a.m. change a diaper to stay awake the whole time. Remember these days. All right. So we're going to go ahead and multiply it across. Hopefully you can see that I'm going to take that 0.1 to the 0.5754. So I'll get 0.0574 minus 0.5754x is equal to x. Combine like terms, and I'll get 1.5754x is equal to 0.0574, or that x equals, who raised your hand? Who's that? Can I see it? Oh, how do I see who raised their hands? Is it under participants? Oh, Kyron and Loban. I assume you wanted to see the math, and Dallas. Is that what those are for?
Yes.
Oh no, I had mine there from earlier and I forgot to take it down.
Okay. All right, so at the end of that, this should be 0.0365 moles of the base, which is, of course, our OH minus, which, of course, is our sodium hydroxide. Right?
Yep.
Okay. Is everyone with me? Anyone not with me? Chef?
I'm good.
Isa?
Peace.
Okay. So now we know how much we have, how many moles of the base we need. So we have 0.0365 moles of the sodium hydroxide. We knew that our sodium hydroxide was 0.4 moles of sodium hydroxide per 1,000 mils. And that's going to give me 91.25 mils titrated in. Titrated into the 100 mils of 1 molar HAC. If you do that, you will end up with a pH of 4.5. Okay. Let's see. It is 11:30. We've been going at this for a couple of hours. The question I have is, do you want to keep going all the way to noon, or do you want me to give you one for you guys to try at home, but it'll require you to think? BR. What's BR mean? Brain is full. Either that is Dallas or that is Garrett.
Not Dallas.
It wasn't me, it was probably Dallas.
Nope.
Oh,
That's
man.
someone else.
Okay.
Go to noon.
So, you know, I should do this one and then send you guys home with the last one. Let's do one. We won't go all the way to noon.
Hey, Forrest, wait, question.
Yeah.
No?
Yes.
Oh, so I keep on trying to look for my lab reports and I cannot find, I can find one. And you said you lost them, so I don't know what to do about that.
You lose them?
Huh?
Is that what I said? Who heard me say I lost it? Oh, I lost the scores. Something happened. I just lost the scores. I didn't lose the labs.
Well, no, yeah, but I lost my labs. I can only find like one, and that's the decayed M&M ones.
Well, it sucks to be you. You failed the others. That's how I roll.
Okay.
Who said that anyway? Who's talking?
Maze.
Maze, when have I ever just done that?
I don't know.
Figure it out with you. Talk to me in an email. We'll figure it out.
Okay, but yeah, I can't. I've looked all day for them yesterday. I was kind of I had like a mental breakdown. I was like, fuck. Or wait, oh, my bad.
On that note, what is your email?
Dallas.
Dallas, if you just log into your school email Outlook account and you type in his name when you go to send to a recipient, he should just pop up without needing his email.
Thanks.
Yeah.
Tristan, have you been losing your gains?
I'm making do. I do what I can, but kind of.
Got to do the push-ups, dog.
What the hell's going on? Did we go sideways? The other thing too, Dallas, you could just Google my name on the first link. You could also just look at your syllabus as well
Which
to
is why
find
we
that.
shouldn't go to 12.
All right, we can end it here, I guess.
No, keep going.
Let's end it here. We'll do a couple more titration ones on Thursday and then jump into pH controlled solubility. I guess everyone is just done. I don't blame you.
What are we doing for lab? I missed that. Sorry.
What do you mean doing for lab?
Like, are we doing labs or?
Yeah. So the rest of the equilibrium labs, you kind of have to be there to do it. We will pick up labs again, meaning virtually, when we start thermo. And so don't worry about labs until we get to thermodynamics at this point.
Okay.
Yeah, we are.
Does that mean this week, next week, the next few weeks?
Hold on. We're not doing experiment 6, the carbonic acid. We're not doing experiment 7, the titration curve. You can thank me later on that one. Ask Sarah El-Khalisi about that one. And we will not do the iron thiocyanate one because basically it was impossible for me to get in to try to do that lab and do it with any justice that you would get anything out of it. You'd either have to sit there and watch a whole bunch of dilutions and putting things into the machine, and it would be a long, boring, hour-and-a-half long thing, or it would be a pointless, like, this was done, here's the result, this is done, here's the result. So I was able to do the thermodynamic labs for you in a rapid fashion. So when we get to the thermodynamic section, there'll be a couple labs for us to take a look at and do the write-ups for. But until we're into thermo, no more labs.
We should all just show up in hazmat suits and do the labs anyways.
Right?
Do you have a hazmat suit?
Yeah, with the gas mask too.
Dallas, of all people, I would have thought you would have had that.
I'm not saying I don't have it. I just doubt everyone else does.
Here, along with his bunker in the backyard with a year's worth of food and a filtration system for air and murder holes for anybody trying to get into it.
Yeah, now that I think about it, I actually think I've seen Dallas on an episode of Doomsday Preppers.
Just saying. Okay, I think we're done. I'm going to stop recording here. I'll just hang around for other questions.
I did actually have a question about the buffer thing.
Okay.
So when we're picking like what substance we're doing for the pH we want, we pick the substance such that the pKa, is close to the pH, and that's so that the pH of, is of course in the buffer region, right?
Yes.
And
so let me go back up to this guy. So we wanted to get a 9.26, right? You see it on the screen there? Am I sharing?
Yeah.
Okay. So I chose the ammonium ion one there because it had a 9.26. Now, does that mean that I could have used the 721 or the 1267? I guess it's just going to be harder to get there. And when you do, let me point this out. If you were to try to get to the 9.6 region, okay?
Mm-hmm.
9.6 region is probably somewhere right about, let me not get my finger on this. It's probably somewhere right about here. How good of a buffer is that going to be?
Oh no, terrible. No, that'd be terrible.
Right, and that's the reason why we picked the pH nearing, or I should say the pKa nearing the pH that we want. Because while yes, you could physically make one right there, it would be a horrible buffer.
Yeah. No, I totally agree with that. My question is, so
that's right.
So when we pick something that's like, when we pick a substance that's a good pick and we do it correctly, and we're like, okay, so, for example, for the pH of 7, and we go with the 7.2 pKa, right? And so the entire point of the buffer is that if we move along it a little bit, it won't change the pH that much. So why do we go to the trouble of getting the 7 exactly instead of just the 7.21 when clearly the entire point of the buffer region is that it's in the buffer region? Okay, we're still within.
That's not a bad question. And the thing is, when we're looking at buffered solutions, almost uniformly, we're talking about biological systems, okay? And biological systems want to be at their pH, kind of, period, end of statement. When we say that the buffer region can go, fluctuate up to like an entire pH point, plus a half or minus a half from your thing, that's the chemist talking. That's the chemist saying, hey, that'll be fine. Biologists would be like, I'm uncomfortable with being that far away. And let me tell you, if you change the pH of your blood by a half pH, you're going to have a bad day. You're going to have a bad day. So the reason why we're trying to be very exact is because if you go to a biochem or biochem engineering or something like that, you're going to want to get these buffers as close as possible, because when you dump your biosubstrate in there, you want it to be like, oh, this is nice. I'm in the nice environment that I like, not into some culture shock of like, hey, you told me this was going to be 7. Why is it 7.15? I'm not happy, and half of me are just going to go ahead and die on you because we're just angry. The reason why we're being so precise is because you might need to be that precise in an application down the road. Now, I think you're a physics major. Is that right, Dallas?
Physics, yeah.
Yeah. So you don't care. You're just gonna do all these approximations and be like, close enough. That's what physics guys do. They're the closest thing to an engineer we have. Engineers are even worse. So
I beg to differ on astrophysics being like, oh, close enough, considering like even a fraction of a decimal point can be thousands of miles off.
You didn't say astrophysics, you just said physics.
Yeah, that's because astrophysics is a longer word to say, and most people don't care enough.
That's whatever you were talking about for you. All right. So I guess we're done here. I'm going to end the recording. Do I want to stop? Man, I hope I'm hitting the right button here.